my presentation screen, but apparently I didn't. All right. So now let's write a really simple factorial function. I guess I didn't actually have to go there. So we want to write factorial. So we're writing a function. So anytime we write a function, we give it a def, we give it a name. I'm going to call it fact because factorial is too long for me to type correctly more than once or twice. And we want to calculate the factorial of some parameter n. Well, if we look at our presentation case, right, what we have is we have the fact that our base case, if we can get down to the case where n equals 0, we know what the value is, right? N equals 0 is defined, 0 factorial is defined as the value 1. So as long as we get down to there, we're good. So let's just code that in first. So if n equals 0, well, we know we're done, right? We know what the factorial of 0 is. It's 1. We can just return 1. If it's not, right, so now we know that n is not equal to 0. And actually, I'm going to, just to protect ourselves, yeah, no, I'll just leave it like this. We'll be smart. If n equals 0, we're going to return 1. If n's not equal to 0, well, what we want to return is we want to return n, right, the current value, and we can look right at our Lecture 23 notes, right, and we look right here, and if n's not equal to 0, then n factorial is just n times n minus 1 factorial, right? So that's really about as direct as you can get, right? So it's n times factorial of n minus 1. Right? Here's the simpler problem. We've simplified the problem by reducing the value of n by 1. We're marching it hopefully towards our n equals 0 case. In the case that n is negative, we're not marching, so we could actually end up with our recursion error there. But if we assume that n's always positive, or if we ensure that n's always positive, that will actually work. Right? And that's just exactly a direct implementation of what is in our presentation, right? If n is equal to 0, we return 1. If n isn't equal to 0, we return n times a simpler problem, n minus 1 factorial. Okay, and we can come into here and we can say then factorial of 0, that should give us 1. Factorial of 1, well, that should be 1 times 1, right? So that 1 factorial should be 1. 2 factorial should be 2. 3 factorial should be 6, right? 3 times 2 factorial. 4 factorial should be 24. 4 times the factorial of 6, right? So it's a really simple function. It counts down, right? The first time through, for example, with factorial of 4, we come down and we calculate 4 times the factorial of 3. Then we calculate 3 times the factorial of 2, 2 times the factorial of 1, 1 times the factorial of 0. Factorial of 0 just returns a 1. 1 times 1 is 1. 2 times 1 is 2. 3 times 2 is 6. And 4 times 6 is 24. Okay? So it's a simple recursive function, and it exactly matches the mathematics of the factorial function. Okay. And we can put some stuff in here if we want. We kind of did this with the blast function already. But we can come in here and we can say print baseline returning wow 1, right? And then we come down here and we can say right, so let's just put in a little instrumentation there. Hopefully that is correct. And now if we come in here, we can do our factorial of 0, baseline returning 1. We can do factorial of 1. Right, that's going to say calculating 1 times the factorial of 0. Right, so we're walking through the recursion. We can do our 2. Right, calculating 2 times 1 factorial, calculating 1 times 0 factorial. And this is the recursion. This is every time we hit one of these, we've gone down another method of this, another level of the stack, and then coming back up, we are kind of unwinding that. All right, let's do 10. How bad could it be? All right. So 10 factorial is 10 times 9 factorial. 9 factorial is 9 times 8 factorial, and so on. When we finally get down to 0, we just return 1, and then we have the information. We can plug the 1 into here to calculate 1 factorial. We can plug the result of 1 factorial into here to calculate 2 factorial, and all the way up until we get times 10 times 9 factorial. All right? Any questions? Can you see the function again, with or without the prints? I'll do it with the prints. So here's the function. It's really pretty simple, right? Actually, let's do it without the prints, just because that's actually even simpler, and it exactly matches the mathematics, right? Here is our check for the base case, and here is the recursive step. Now, of course, if we're not careful and we give it a negative number, the way this is written, that's going to give us an error, right? Maximum recursion depth exceeded. Okay? If you're getting into multiplying an int by a none, then you are probably missing a return either for the base case or for the factorial itself, right? You need this return and you need this return. All right. I'm going to move on while Kristen kind of handles that. We're not doing too badly, but this is always kind of a longer lecture. All right, so let's look at the Fibonacci sequence. I'm not actually going to do this one for you because there are examples of this one in the exercises today. But Fibonacci sequence recurses on 2 values, right? We have to know what the value of Fibonacci of 0 and Fibonacci of 1 are. Well, we can say that Fibonacci of 0 is 0. Fibonacci of 1 is 1. And then if we specify those 2 base cases, right? We have to handle 2 base cases, either 0 or 1. If we specify those, then the next number in the sequence is equal to, n, value n, is equal to the value at n minus 1 plus the Fibonacci of n minus 2. Okay, so 0 is 0, 1 is 1, 2 is 0 plus 1 is the Fibonacci number of 0 plus the Fibonacci of 1. Fibonacci number 3 is Fibonacci 2 plus Fibonacci 1. Fibonacci 4 is Fibonacci 3 plus Fibonacci of 2, and etc. And it's really a pretty simple function to write, and you can write it recursively, or you can use a list. And what I want to tell you is, as you get up here, right, in order to calculate, for example, the Fibonacci number of 10, let me see if my camera is still on. Because this is something this is one of the dangers of recursion, is that sometimes there's these complications. This is really easy to specify in terms of the mathematics, and it's really easy to convert that into a recursive function. But one of the things you want to look at is, what does this mean when you actually start evaluating the algorithm in terms of efficiency, right? So if we want to do the Fibonacci number of 10, right, we have to calculate the Fibonacci number of 9 and the Fibonacci number of 8. Right? And then to calculate the Fibonacci number of 9, we have to calculate the Fibonacci number of 8 and the Fibonacci number of 7 and 7 and 6. I'm going to leave the F's off for now, from now on. And then 7, 6, 6, 5, 7, 6, 5. No, I'm sorry, 6, 5, 6, 5, 5, 4, 6, 5, 5, 4, 5, 4, 4, 3, 5, 4, 4, 3, 4, 3, 3, 2. And what you should be seeing here is that as we kind of go down through these levels, you know, just focusing on 4, for example, at this point, and we will call it more down below, to this point we've already calculated 4 6 times. We've calculated 7 1, 2, 3 times. Right? We've calculated 6 1, 2, 3, 4, 5 times. Okay? The point is that we're calculating the same values over and over again. Which means that there is a lot of wasted calculation. Let me see what the actual exercises have here. Yeah. So we're going to have you implement, this is the direct implementation. Base that off of exactly this argument. Yeah, exactly this recursive structure. And then we want you to, of course, again, you can't see that. Right, so we're going to ask you to calculate the Fibonacci number 2 ways. The first one, we want you to use this recursive function to calculate it. And the second way is think about creating a list. Instead of using recursion at all, use a simple for loop and keep the values in a list. And then at the end, you know, submit your answers, but then try running them for numbers. I think if you go up to 10, you will probably see enough of a difference that you won't want to go much higher. Although maybe I may have gone higher. Anyway, you know, just kind of pay attention to that, because that's one of the things that can be very dangerous about recursive functions. Is recursive functions are a nice mathematical formulation, but sometimes something as simple as this recursion can hide a lot of actual work that needs to be done multiple times. Recursive calls oftentimes have more overhead. So although even when they don't run into this combinatorics problem, when their running time is no different than a good for loop implementation, they can still have running time issues that just because function calls take longer than running through a for loop. And this says, we'll see in class, well, the Fibonacci you guys have to do. Let me convert the factorial to a simple, let's do factorial serial. I'll call that just F. So let me get down to we'll do def F for factorial serial, right? So what you're seeing here is we're doing a simple, our recursion is really very simple. All we're doing is counting down by 1. So if we just count up the other way for val, let's say value equals 1, for v in range n+1, right? Value times equals v, right? So this is we're going to start out at 0. We're going to start out as, for the 0 case, we're just going to return 1. For 1, we're going to return 1 times the 0 case. For 2, we're going to return 2 times the 1 case, etc. Just a simple for loop. If we want to keep all of these, we could even do something like that. In fact, let's do that. That's kind of a cool way to do it. It's not normally the way I do it. At the end, what we'll have is we'll have a list of our factorials, and we can calculate it right in place. So we can say fact dot append v times the previous factor, fact sub v minus 1. Okay, so this is a non-recursive one. What we're going to do is we're going to build up the list, and then at the end we'll just return fact sub n. I think this will work. Let's find out. Fact 0, f0. I don't know how to get out of this now that I've made the mistake. Oh. There we go. That should be. Get our syntax errors out. Try that again. Right? 1, fax 1 should give us a 1. Fax 2 should give us a 2, 3. Right, so this is just a simple way to convert our recursive factorial into a linear factorial. And you can do something similar when you're right, there's the recursive one, and then there's the non-recursive one. Except that this should be fax instead. Let's see. There we go. There's the non-recursive one. So you should be able to do something similar when you do your exercises. Okay. We've got a few more minutes here. I'm afraid we're not going to get through most of these, but I do want to quickly look at a few things. Recursion is important because it allows us to, for one thing, it matches a lot of these mathematical definitions, and oftentimes, even with the Fibonacci sequence, it's really easy to see how to do it using recursion, because once you understand recursion, these are recursive algorithms. So it makes it easy to understand and easy to program. Once you get them done and you find out they're not, if you don't need efficiency, if they're efficient enough, you just can stop there. But if you need speed, then you can find a way to do it non-recursively. And remember that recursion at its base is implemented by using this whole stack thing, which is just an artifact of somebody's computer operating system program. So at the worst, you can always convert a non-recursive function into a recursive function into a non-recursive function. Whether you can improve on the time bounds is maybe a little bit different. Some things like flattening a list or traversing a tree are still hard. I am not going to be able to do all three of these versions today. I think I can probably look at these a little bit tomorrow, but I do want to quickly give you, let's take a look at least at the Sierpinski Triangle. I think we have that in the code listed in class, because one of the things you're going to be asked to do, this is the Sierpinski Triangle is actually a fractal, and it uses TK inner, and it's something that you're going to be asked to do something similar to this in your lab this week. And we'll go into it more on Thursday, I think. But let's just take a quick look here at the code. Most of this code is just setting up the TK inner stuff. You don't have to be worried about that. But I want to talk about what this code actually does. So the Sierpinski Triangle starts off by drawing. Now you've gone too far. There you go. Starts off by drawing essentially a triangle, a big triangle, all in red, and then it puts a white inverted triangle in the middle of it. And then as you go down, it takes each one of the red triangles and puts a red triangle in the middle of it, right? And then if you go down further, it takes this red triangle and puts a red triangle in the middle of it, or a white triangle in the middle of it, right? So it's a recursive function. It recurses on levels. And yeah, so what I just want to look at is I want to look at how this is actually implemented. You can ignore most of this stuff. We'll get into this when we talk a little bit more about TK inner. But where do we see the... Here we go. So here's the recursive part. Draw triangles is the recursive function. Okay, you'll create a polygon, right? This is the base case, essentially. This is, you just draw a polygon at the current x and y coordinates with specific line lengths. If you're not at the end of your depth, right? So this is the base case, draw a single triangle and return. If you're not at your depth, then what you'll do is you'll call okay. Yeah. If that's not the case, then you put the white triangle in the middle, and then you'll call yourself again on each one of those red triangles that remain. Okay, so going back to our, dang it, going back to our thing, we start off, we draw a red triangle, then we draw a white triangle in the middle of it. If we haven't bottomed out, if we bottom out, we would just draw the red triangle. If we haven't bottomed out, then we'll draw this white triangle, and then we'll recurse on each one of these red triangles. Okay, and that should be pretty much what the Sierpinski Triangle does. And let's just see how this looks. Hopefully this will come. Here it goes. And you guys probably can't see this, so let me. There we go. Right, this is a depth of 2. We can decrease our depth to 0. That's our minimum level. If we draw that, that's a 0 level triangle, right? If we go down depth of 1. Right now, we're going to go through, and let's slow this down. When we draw the level 1 triangle, we draw the red triangle. We draw the white triangle in the middle.
No! Professor, we can't see it. Sorry.
Maybe I didn't turn it on. Thank you. There we go. See it now? Okay, let me go.
Yep.
Okay, thank you. Thanks. Okay, so level 0, we come down here, we draw a red triangle. Okay? And now I've lost the triangle. There it is. If we increase the depth to 1, we're going to draw this triangle. We're going to draw the white triangle in the middle, and then we'll recurse on each one of these upper 3, but we'll be at our depth, so we're only going to draw red over red. Okay, so now we've drawn the white triangle in the middle, recurse down into our draw triangles 3 times, specifying this, this, and this. We stop. If we increase the depth 1 more, now we're going to draw, the next time through, we'll come back down into here. We'll draw another white triangle in the middle and recurse on these guys as well. So anyway, I think I've kept you long enough. I will hit flattening a list and a recursive merge sort next class, and we'll go more into this whole thing. But take a look at your lab. Use your TAs, use your mentors, talk to them. All right?